Hello there, here we are with yet another book review. Today we will be talking about Why Machines Learn, the Elegant Math Behind Modern AI, a book by Anil and Ananthaswamy. So let's get cracking. Now, the first thing I want to say, if you get one thing from this video review, it should be this. Read this book. This is a really good book. This is a gem of a book. What's it about? Well, the title says everything. This is going to give you the slightly technical baggage of how machines learn, of how modern AI, including ChatGPT, works. So you could classify this book as this is what we generally call not math, science outreach. Yeah. And so it's for a general audience. It has a lot of formulas in mathematics, and that makes it a bit unusual even in this format. Yeah, you will know the famous Stephen Hawking anecdote that his editor told him that for every formula he included in the book, he lost 50% of the readership. And this also leads to popular science books and popular math books being very wary of using a lot of technicalities or a lot of advanced mathematics. So you have books that are science outreach that have a wide spectrum. Some are very readable, very light, very accessible. Some are a bit more demanding. So I'd say Ananthaswamy's book is in the upper end. This is not a light read. You will need some mathematical prerequisites, which we will talk about in a minute. It's dense. You will have to really pay attention to what you're saying. That doesn't mean that it isn't entertaining. It is. It's also very enlightening. But it feels like optimized for being a second read, just short of a textbook about machine learning. What would be the first read? Well, this year I read another book. This was my first book about machine learning, The Alignment Problem by Brian Christian. This book pairs, they pair wonderfully together. They should be sold together. So like this book gives you a general, more accessible, less technical history of machine learning and its main steps. And it's very entertaining, very anecdotal, and it gives you the mental map. Some limitations it has. First, it was published in 2020, so nothing about the LLM explosion. And the second is that although it's very good at introducing you the main changes, the main algorithms and developments, it explains them in a very, very generic and unspecific way. So a lot of the time, like you read something here like about the perceptron or about multiple layered neural networks and about machines being able to predict and to learn. Yeah. And you just start thinking, okay, I get the general idea, but how does any of this actually work? So do you want to know how it works? This book tells you how it works. It will give you the math, the algorithms, everything you need to know about how it actually works. So this book is shameless about using mathematics, and almost, I wouldn't say almost every page, but this is about the mathematics of machine learning. So you've got lots of equations, lots of formulas, linear algebra, other stuff, matrices. This is meaty. Prerequisites. So you need some background. The author, I think, mentions in the first pages what the minimal background is. I think he undersells the difficulty. I mean, the math is occasionally harder than advertised, especially in some of the proofs. But basically, if you have like a good level of high school math, especially in statistics, some ideas about linear algebra, a course in linear algebra would help. And maybe knowing a little bit of computer science, which was my weakest point. But with those things, you have no problem reading the book, or you should have little problems understanding most of the book. As I said, it's really illuminating, and I really can't fault this book for anything. Like, if I had to say what are the negative aspects of this book, it doesn't really have any. The math is dense, but it's interesting, and the point of this book is explaining the math. And it's, as I said, it's not dense in the sense of it's not graduate math. You can get it if you have the background that the author mentioned. But you have to pay attention. You don't read this like you read a novel. You don't even read this like you read the alignment problem. You have to read it, stopping, thinking, maybe going over the section again a little bit. Like you read, not exactly a math textbook, but in between the space of a popular math book and a very, very light and accessible textbook. It's in between. Okay, what else can we say about this book? Yeah, I wouldn't quite complain about it, but in the last chapter, I think it talks a little bit about the typical complaints that people have about the dangers of AI in issues of equity, inclusion, fairness, avoiding biases. I'm not too interested in those issues, and I'm very skeptic about some of the political uses that those sorts of arguments um, generally generate. Christian talked much more about those topics. He went down the rabbit hole, but I think he did it with tact, and yeah, it's not something that I'm really interested in. I don't think that's a big gripe in this book, but it's a minor one, just a minor quip. Okay, so that's the general impression that I wanted to transmit of this book. And now, if you want to know more about the book, you can continue listening. I will now make a little exploration of each of the chapters. Yeah, there are 12 chapters in this book, so I'll make a brief summary of each of them. So the first one, desperately seeking patterns. Yeah, this one sets the stage for machine learning. It introduces you the perceptron, which was designed in the 50s, 60s. Here it speaks more of the perceptron as an algorithm, whereas Christian's book actually dealt more with the machine that was built using the perceptron's algorithm. So the core idea at machine learning, and therefore at all that this book talks, is starting with finding patterns in labeled data. But this is actually the idea of supervised learning. And it tries to show you how you can design an algorithm that can learn weights and modify weights to model linear relationships. And the key concept there is linear separability, the ability to draw a line or hyperplane that separates the data into two categories, for example, like you have here. And yeah, this is one of the first uses of the perceptron. So the perceptron is like really explained in detail. It's explained in quite a lot of detail in this first chapter. I'm not sure if it's in the first or in the second, or if they both overlap. So how the perceptron works, I'm trying to find the picture here. Yeah, I think, yeah, here it is. Yeah, this is exactly, so this book tells you, you know the perceptron? This is the perceptron, and this is how it works. So the perceptron has like some input values, yeah? These values, W1, W2, W3, they're the input. They could be features like height or weight or pixels. It multiplies each of them by a weight. Yeah, X1, W weight 1, X1, weight 2, X2, and so on and so forth. And then it passes the results through a function, a threshold function, G, yeah, which, so this is the first function, and the output goes to, the threshold function is F. So you first get this data, you pass it to the first function G, which calculates the weighted sum and multiplies each by the weight, and then it goes as the input of a second function F. And the second function basically has only two possible outputs. If the result of the weighted sum is greater than 0, it outputs one class, which could be, I don't know, 1, which would be yes. If not, it outputs another, no, so let's say -1. Now the perceptron learns by adjusting its weights whenever it makes a mistake. And we know already when we're feeding in the data and when we're seeing the results if it's making mistakes or not, because the data is labeled. This is what we mentioned before. This is supervised learning. Yeah. So like the machine can change you give this data x1, x2. The machine gives you a wrong y, a wrong output at the end, and we can say no, this is wrong. You have to correct, and the correction is changing, adjusting the weights. Yeah. moving the decision boundary a bit after reaching correct classification. And you do this a lot, and it ends up making a very good boundary. Yeah. If and only if the data is linearly separable, if you can actually make a straight line that separates the data into two sections, or if it's in multiple dimensions, a hyperplane that cuts the data into two baskets. Yeah. So this is the ancestor of modern neural nets, but it already introduces the key ideas like learning from the data, representing knowledge as weights, and making predictions via dot products and thresholds, which is linear algebra. Okay, so this was chapter 1. Chapter 2, we are all just numbers here. This gets into the linear algebra part. This is linear algebra 101, introduces vectors and dot products as the basic language of machine learning. It explores a geometric view in which you can see data points as vectors in space. And their classification is about which side of the hyperplane they fall on, as we just mentioned. The dot product measures alignment between the weight vector and the input. And this helps build up to understanding how the perceptron makes the decision of dividing the plane into and the data into two sections, into two baskets. Okay, chapter 3, the bottom of the bowl. This introduces you to optimization and calculus. The key idea here is gradient descent, which is a concept that appears all the time whenever you read anything about machine learning. This chapter explains you what gradient descent is. So the bottom of the bowl here is a metaphor for a loss function. So like you want a function that finds the lowest point, because the lowest point here is the minimum error from what the function that takes in the data, as we saw in the perceptron, and chugs out a result. So you need a loss function that updates the function, the initial function you're creating, so that it minimizes the errors, the discrepancies between, this is again supervised learning, between the relations you have between the data and the outcome. So, well, this chapter is really calculus heavy, talks a lot about derivatives. Here you have gradient descent. You start with this, and then you update with this algorithm. If the function you are working with is concave, it has a minimum. So there will be a minimum error that the function, through its algorithm, can go down to, the loss function. And this really explains how networks are really trained when you're doing machine learning, which is gradient descent, minimizing the error from what the function predicts and the result, the correct result that you already know because of the training data. And then the trick is then you add new data, and based on the training and on the function that it developed, it should be able to put the data in the appropriate basket. Okay, chapter 4. In all probability, this is a probability chapter. It's basically an introduction to probability and Bayesian inference. You get the staple stuff in such a chapter, priors, likelihoods, posteriors, Bayes' theorem. Algorithmically speaking, it introduces the notion of the naive Bayes classifiers, which are optimal algorithms if you can employ them for classifying information. And yeah, you can see when I talked about in the previous chapter about the loss function, about the machine updating its information with new data, this sounds very Bayesian. Yeah, like the machine seems to be updating its beliefs based on the corrections you give it. Okay, chapter 5. Here it is, birds of a feather. What was this about? Yeah. Okay, so here you start exploring unsupervised learning, especially clustering. So what happens if you want the machine to classify stuff and it's not labeled before you start? Well, the way you start moving in this direction is, so like you get learning algorithms that, for example, cut the hyperplane, but not with a line, but with a curve. And you have this is the NN, the nearest neighbor algorithm, which is very good at that. As you can see, it separates the data by checking at which are its closest n elements. The CAD is not a straight line. Yeah, it's going to be different. Yeah. Okay, what else does this? So yeah, the KNN rule is as good as the Bayesian optimal classifier that is shown here. Also, Shatter starts explaining the problems with dimensionality. Sometimes the data, we were talking about data being vectors in some n-dimensional space. One way of representing this is with matrices. So the problem sometimes is if you're working with data, well, you have a lot of parameters. Like imagine you have you're analyzing the patients who died from heart attacks in a certain hospital in a certain year. And you can make a table. Each patient is a column, and each row is one characteristic of the patient. Age, for example, previous heart diseases, whatever. So one thing you can do here is you create with this table a big matrix, which could have tens, hundreds, maybe thousands of rows. Doing operations with numbers that are so high is going to be difficult. So there are methods, there are algorithms that allow you to collapse spaces and go to lower dimensions so that you can do the calculations in an easier way. And sometimes you can do the opposite. You can go into higher dimensions and it proves really useful. Okay, the next chapter, there's magic in them matrices. So this explores matrix transformations, which are the heart of neural networks. Each network is like, each network layer is just a matrix operation plus nonlinearity. You get a good explanation of eigenvalues and eigenvectors here. There's the concept of principal component analysis, which I think is explained in this chapter. I think it was in this chapter. So the idea there is what we mentioned before, reducing the dimensionality, but you preserve directions of greatest variance in data. Okay, and the PCA helps you to compress the data while retaining the structure. And this is useful for visualization and efficiency. Okay, chapter 7, the great kernel rope trick. Yeah, so this explains a trick that is central to support vector machines. Sometimes data is not linearly separable, and then that's when one of the things you can do is try to map it into a higher dimensional space where the separation becomes possible. And the trick there basically is you use these things called kernel functions, which are very nifty because the problem with higher dimensional spaces that we mentioned is the calculations might become atrociously complicated there. But with a kernel function, you don't have to compute directly in the higher dimensional space. You design this function so that the results they give in lower dimensional space are the same as they will give in higher dimensional space. So it's a nifty trick that saves you a lot of work. Okay, more things. Next chapter 8, with a little help from physics. So this basically explains you the actions of a physicist called John Hopfield and his development of something called Hopfield networks, which were connected with, they were the attempt at how can we say, replicating memory, but for machine learning algorithms and models. So these networks use an energy function. They evolve towards low energy stable states, which represent memorized patterns. Another concept that is explained here is Hebbian learning, neurons that fire together, wire together. And yeah, generally, it's a very interesting chapter that shows you applications from statistical physics to machine learning. Okay, and one of the examples of how this works is like detecting numbers or training a machine to detect numbers, including with background noise. Okay, chapter 9, the man who set back deep learning, not really. The title is ironic. The man is George Sibenko, I think. So, one thing I skipped that I should have mentioned in the earlier chapters was that the perceptron came into trouble because this MIT scientist, Marvin Minsky, wrote a book saying that perceptrons had very big limitations. There were problems that they couldn't solve. And so they were a dead end. And one possibility of breaking out of this was, and that was the path that would be followed, is maybe a one-layered perceptron-like algorithm cannot solve certain problems, but maybe if you have different layers instead of one, you can solve this. And that was what happened in the end with multiple layers as a way of solving the limitations of the perceptron. But this man, Stebenko, he basically proved the universal approximation theorem in 1989. And what he proved was actually that even with only one layer, just one hidden layer, you can approximate any continuous function on a bounded domain given enough neurons. So this overturns the assumption that neural nets were too limited, but it didn't move the focus to multiple layers, which is how neural networks work now, with lots of hidden layers. Okay, this was chapter 9. Number 10, the algorithm that put paid to a persistent myth. Okay, so this one is about backpropagation, which is an algorithm designed by Rumelhart, Hinton, and Williams in the late 80s, 90s. So backdrop is an algorithm for computing gradients efficiently across multiple layers using calculus, so basically using the chain rule. And the myth that it debunked was that deep neural networks couldn't be trained in practice. And it also touches on other things like vanishing gradients, later solved by innovations like ReLU, yeah, and better initializations. We're close to the end now. Chapter 11, The Eyes of a Machine, is interesting. This dwells about software for image recognition. And it introduces also a key idea, which are convolutional neural networks, CNNs. These use filters to detect patterns, like edges or corners or textures. And convolutional layers slide across images, pulling the layers down and keeping key features. And convolution allows you for building hierarchies of abstraction from more simple to more complex patterns. And they were inspired by the visual cortex, I think, which does this thing like it pulls in impressions to some neurons, and then from those specialized neurons, it goes further down the line. And finally, chapter 12, Terra Incognita, is the last one. It looks at the cutting edge when this book was published, which was last year. So transformers, large language models, and possible future developments. One of the interesting things it talked about was whether traditional machine learning theory can still explain what these systems are doing. Generally, in the past, you had mathematics leading the way to the technological developments, and now we might have reached a stage where it goes the other way. It's the chapter that also mentions issues about bias, governance, interpretability, and suggests we may need a new theory. So to conclude, as I said, this book makes abstract concepts click. It's really good. Reminded me a lot of another book, Eugenia Cheng's The Joy of Abstraction, which tries to do the same thing for category theory that this book tries to do for machine learning. And it's not easy, but it's worth it. And especially if you're math literate and want more than a surface level ML hype. This book will show you not only why machines learn, it reveals the structure behind how machines learn. And yeah, that will be all for today.